Hi there, everybody. I'm making this video to help walk through the table in the layer silicates section of CrystalMaker Assignment 3. So first things first, make sure to download the unknown structure files from this folder here. And this is important because these files are not going to be in your CrystalMaker library. They are specifically modified by us to make sure that the mineral name is not associated with the file so that we can walk through the process of determining an unknown mineral, the group of an unknown mineral. Okay? Once you have those downloaded, you go to File and then Open, and then navigate to the location wherever you save the file on your computer, and then open the unknown file. So, for the table, we're going to use a few pieces of information to determine the possible group or subgroup of the unknown minerals. Notice you might not be able to determine the group name specifically, but we're going to get as close as we can. Okay? And make sure that you have your book available. We're going to be using table 22.5 to help us determine this. So, I have a couple examples loaded up to just show how the thought process works, and then I'm going to run through an unknown that you will not have access to, again, just to show you how to attack an unknown. Okay, so let's pull up the CrystalMaker files that I have loaded. So on the left I have muscovite, and on the right I have chrysotile, or white asbestos. So these structures should look a little different right away, and the first thing we want to notice is that both of these have silicon. Both of these have silicon in the, the tetrahedral sites here. So the purple are silica tetrahedrons, and then on the left we have blue, kind of sky blue aluminum, and on the right we have this golden yellow magnesium. But crucially, we should notice that the silicon are tetrahedrons. You can see that they are triangular-based pyramids, whereas the aluminums, the blue, are two square-based pyramids end to end, or base to base. So what that means is they make an 8-sided shape, or an octahedron, not a tetrahedron, right? So let's reorient now that I've tilted, scale, and center. And we're going to be looking at the same thing here in chrysotile. We have triangular-based pyramids representing our silicon, and we have 8-sided square-based, two square-based pyramids representing our magnesium. Those are the octahedrons. Reorient, scale, and center. All right, so the first step, the first thing we want to do in our table is determine is the mineral 1-to-1 or 2-to-1. And to determine that, we need to look at the tetrahedron and octahedrons. And specifically, we need to look at the sequence in which they occur in the mineral. So in muscovite, let's have a look at it. I see, reading from the top down, I have a tetrahedral layer, I have an octahedral layer, followed by another tetrahedral layer, and then there's a potassium, these purple spheres, and then I have another tetrahedron, octahedron, tetrahedron, and it just repeats. Now let's look at chrysotile. We have an octahedral layer, and then a tetrahedral layer, and then a new layer appears with nothing in between. Then an octahedron, then a tetrahedron, then a new layer appears, octahedron, tetrahedron. So each time there's a gap, that means there's a new layer. And the same thing with muscovite. Every time potassium shows up, that means there's a new layer. So you can sort of think of muscovite as like a sandwich, with silicon being the bread and aluminum being whatever you put on your sandwich. And then chrysotile, I don't know, avocado toast or something, where you have bread on the bottom and then something on top of it. Okay? But crucially, with chrysotile, you don't have two tetrahedrons for every one octahedron. Where have I heard 2-to-1 before? That's on this table, right? So if we have 2 tetrahedral layers and 1 octahedral layer, that means you have a 2-to-1 relationship. And so muscovite is our 2 tetrahedrons to 1 octahedron, so it is 2-to-1. It's our sandwich. Chrysotile, we can see we have 1 octahedral and 1 tetrahedral, so it's 1-to-1. 1-to-1. It's our avocado toast. All right, now we need to determine what the interlayer cation is, or if there isn't one. And so what do I mean by that? I mean, in between the layers, remember I said that every time you go tetrahedral, octahedral, tetrahedral. Another way to say that is TOT. Every time you go TOT, there's going to be a new layer starting. So we go TOT, and then a new layer, TOT, new layer, TOT for muscovite. In between those layers, I do, in fact, see a cation. I see potassium. Potassium's a cation. Whereas in chrysotile, I do not. I see OT blank, OT blank, OT. So muscovite, it has an interlayer cation. That interlayer cation is potassium. We're going to go in here. We're going to say potassium. And chrysotile does not have one, so we type in none. All right. Next up, we're going to have to reorient ourselves to determine dioctahedral or trioctahedral. So if you assume that this has something to do with the octahedral layer, you'd be right. What we want to do is we want to rotate our crystals 90 degrees in the positive X direction. So, bam. Do the same here. Rotate 90 degrees up. And now we are looking at our crystal, not sort of like tall up and down. We're looking at it long. All right. So since I said we needed to look at the octahedral layer, let's turn off the silicons just to make this a little bit easier. And in the case of muscovite, I'll also turn off the potassiums. Do that over here. Chrysotile. Turn off the silicons. Okay, so we have aluminum on the left, magnesium on the right. Now the way we determine is this dioctahedral or trioctahedral is by understanding that there are 3 possible sites for an octahedral structure to fit into any given mineral. There are 3 possible, and a dioctahedral mineral will have 2 of those sites filled, whereas trioctahedral will have all 3 sites filled. And so if you have something that's a layer, like a layer silicate, if you have a layer and it has 3 possible sites, and if you fill all 3, that means you should essentially see just a wall of octahedrons when you're looking at it down like the barrel of the octahedrons, right? Where they're flat, not you can't see the layers, you're looking like down on top of the layers. Like we are now. So on the left, muscovite, it sort of looks like it's totally a flat wall of octahedrons, but let's rotate slightly. And we can see that there are gaps in between. So if we sort of rotate and look a little bit on the side of our long structure, we can see that there are these holes in between the octahedral sites, right? You can see through them. They make gaps. Now let's rotate chrysotile. No matter how we rotate it, there's no gaps in between the octahedrons. That means that all 3 sites in chrysotile are filled. All 3 octahedral sites are filled. In muscovite, only 2 of them are filled. And from there, we can determine that muscovite is dioctahedral, di meaning 2, because it has 2 of the octahedral sites filled, whereas chrysotile is trioctahedral. Tri meaning 3. All 3 octahedral sites are filled. Okay? So at this point, if these were unknowns, we would then resort to our table 22.5, to help us determine the possible groups. We already know that these are muscovite and chrysotile, but let's have a look at the table anyway. So let's keep our assignment sort of up off to the side here. Okay, so starting on the left side of the table, our layer type. We have a 2-to-1 in our first row. Great. Our interlayer. Now, we have to determine here, is our interlayer hydrated or non-hydrated? Are the cations hydrated or non-hydrated? And so let's go back and have a look at muscovite real fast. If we open the inspector, we see that there are OHs, there are hydroxides. So let's turn everything back on here. Have a look at our interlayer cation. So there it is, there's the potassium. And let's turn on the OHs to see if they are hydrated. And if they were hydrated, they would have hydroxides attached to them. They do not. Okay? So we are in a non-hydrated cations. Remember, we're in 2 to 1. We have non-hydrated cations. So at the very least, we know we're in the true micas group, but we also know that muscovite is dioctahedral. So we are in the dioctahedral micas, and there it is, muscovite. So we did it right. Let's follow the logic again. Chrysotile, it's 1 to 1, which means that its interlayer is either none or it has H2O only, and we determine that there is none. There's no interlayer cation. So its group is, at the very least, the kaolin serpentine groups. But we know that... excuse me, one moment. Yeah, sorry. I was just not scrolled all the way over. I was curious why I didn't see it. So yeah, we're in the kaolin serpentine group. We know that our subgroups, it's either serpentine or kaolinite, but since we already know the mineral, we know that we're in the serpentine group and that we are looking at chrysotile. Okay? All right. Next up is the unknown. And this one I did fail to load, so give me a moment. Okay, so now I have loaded my unknown. So I see a few things right off the bat, but let's look at our table and see what information we need. I need to determine, is the crystal 1 to 1 or 2 to 1? I need to determine whether there's an interlayer cation. If there is, I need to say what it is, or say that there is none, and then determine dioctahedral or trioctahedral. Okay? So right off the bat, I can see that there is a tetrahedral layer, an octahedral layer, and another tetrahedral layer. So TOT. From my previous example, I know that means that this is a 2 to 1 structure. I can also see that in between each TOT layer, there is a cation. Again, it is potassium. I can see that up in the top right of my CrystalMaker window. Potassium is the purple. Now I need to determine dioctahedral or trioctahedral. And just to do it, let's turn off potassium. Let's turn off silicon. Rotate. I can see that no matter what way I try to orient this crystal, I just have walls of octahedral sites, right? All 3 of them are filled, so I know that this is a trioctahedral mineral. Okay? Now let's quickly determine, are my interlayer cations hydrated? Well, I don't have any hydroxide groups in my atoms, so I don't think it can be. So let's have a look at the table. So remember, we're in 2 to 1. Our layer type is 2 to 1. Our interlayer cation is a non-hydrated cation. So very likely I am in the true micas, and I am in the trioctahedral micas. right? So, at the very least, I can say that I am in the trioctahedral micas subgroup, and that's as specific as I can be. So we'll go in here and we'll say trioctahedral micas. And there we go. So follow those steps, figure out your unknowns, fill out this table. Good luck. I'll see you in the next video.